Hi, good morning. And this is Dr. Mohammed El-Hadedy. Today, I'm actually gonna go through our project Ptah, which is basically teaching computer architecture through natural language processing control drones with Edge AI and Kubernetes. This work has been done in collaboration with Dr. Benny Shang from the U.S. Navy and Dr. Wenmei Hu from the University of Illinois at Urbana-Champaign, a coordinated science laboratory. So to go through the work, we will find out that, our overview is to aim on building a new computer architecture curriculum that will be integrating both edge AI and edge computing in general, merging the natural language processing within advanced, which is basically they call it physical agents control systems, because nowadays AI most likely working with software agents. So the objectives of the work, as you can see, have been distributed in a multiple bullets. So, applying the techniques of natural language processing, which is basically looking into the spectrum of natural language processing from Mistral, BERT, Llama, and all of those pre-exist trained models and making modifications by adding the required network layers that it will allow us to build like an API between the drones and the final customers who are going to be having interfacing with audio, or it could be a video with facial recognitions, or it could be just like typing in a keyboard. Also demonstrating the AI capabilities on the distributed systems. And, we know that, in AI, we have training phase and we have inference phase. And, training, it needs like a massive amount of computing, which is basically using like a GPUs like L40S, higher versions of GPUs, Volta, or whatever, exist in the market at the moment for like supporting training. But in the curriculum, we are looking more into the inference accelerations. And in inference accelerations, one of the capabilities is to learn distributed systems, which is tiny little devices that has limited computing. But using all of them in orchestrators and the top of them, that would be the best for the student learning outcomes. And of course, some of them is like Jetson Nano, Jetson Orin, Jetson Orin Xavier, Jetson Orin NX, and of course, Raspberry Pi, which is basically commonly used in our curriculum for teaching computer architecture, at least in Acapulco. Employ also Kubernetes, as I mentioned in the early, is very interesting and important because, end of the day, I can scale up, and that could be on a drones. And, what type of devices that can be. And end of the game, we want hands-on, which is preparing the students to understand the theoretical part of the deploying applications on computer architecture, and that's actually going to be supporting computer architecture classes. Then looking further to the related work and why Ptah is really quite different. So if you look into the educational perspective of computer architecture, you will find majority of the courses, even in the top tier institutes, looking into simulation tools, or even some isolated lab experience, exploring memory and of course CPU scheduling and using BERT or VERF and all this interesting stuff. However, looking into the whole entire system is not really into the pictures. That's why Ptah is targeting to build the system by your hand, making mistakes by your hand and fixing the mistakes by your hand through the semester based, which is the 15 weeks, or based on the quarter, maybe like some of other universities. And the top of that, Ptah is unique in integrations. Ptah is actually helping people to work on real-time control systems, AI influences, and even looking into the security aspects. If you already have a bunch of drones running a scalable orchestration like Kubernetes, you need the communication between these drones to be secure. So we are actually touching the architecture of the post-quantum crypto on actual hardware and how we deal with the memory optimization, especially post-quantum crypto is one of the applications actually need a lot of memory. And exposes actually how we're going to handle the data from the stack, from the users to the NLP model to the K3S, which is one of the Kubernetes orchestrators, lightweight versions that's actually targeting the small and tiny and edge computing devices. Okay, now if we look into why it matters, it's gonna be concept of teaching even the students what will happen in a tiny process and transactions for the cache hierarchy, scheduling, latency. Latency is very important because we keep adding into the stack. That means every single piece is gonna add more latency and more response time in a way that the decisions until the propellers of the drones it will be affected and turning on. Of course, students will be learning debugging, which is a big problem even in the curriculums. I noticed that by myself while I'm teaching. It's very tedious. It takes a lot of time, which is basically it's make students actually fully understanding that they're actually future engineer and scientists, and they need to work by their hand to figure out the best solution for that. Overview. So again, Ptah aim on building, applying NLP. Ptah is working on demonstrating the capability of AI. Ptah is learning on using for Kubernetes distributed scalability system. Ptah is looking also for hands-on for computer architecture. Okay, now system overview. So if we look into the system overview, we will find out that NLP as an input is going into the microservice. So what does it mean? So we add the layers that it need to be added to the pre-trained model like BERT, and that's basically what we already have done in the US Navy grant that we received for doing this work. Then we have to take all the dependencies of the operating system around us into consideration and build a pod. And that pod, it's a kind of Docker. They're gonna go inside the orchestrators, and it will be signed. Then drone A will sign it. Then drone B or the UGV is communicating with it will verify, and after the verification, it will be start sending that pod to another one and building a kind of like a chain between of the drones, so we can build like a swarm of drones that's orchestrated by the Kubernetes to distribute more of these pods. Then, if we look into the hardware layout, we'll find out we keep saying edge computing, but what edge computing part we use? So if we look into the whole entire spectrum of the edge computing for teaching, you'll find out Raspberry Pi is really quite famous to be added in, for instance, a company created in 2015 in supercomputing, something called Bitscope, which is like a racks of Raspberry Pi supported by SSDs for making massive computing using Kubernetes and orchestrations like K8s. But there are some other companies like DeskPi 6, Super 6. There's another company called Turing Pi. There is a company actually located in UK built ClusterHAT, which is basically a little ClusterHAT that it will be laying in the top of Raspberry Pi 4 or 5. Then that will allow you to have a multiple of the Raspberry Pi ZW to be like a multi-nodes running in parallel. So, looking into that, so you will find out that, Turing Pi, which is a company I mentioned earlier, is supporting Compute Module 4, is supporting a new version they already made in their house. It's called TRK1, which is RISC-V Rockchip architecture, which is interesting for computer architecture to learn the differences and benchmarking between of them, and even, with running Jetson. Of course, making the pods talk to each other. So we need MQTT blocker and message queue handler. So that's actually a part of the distributed system learning curve. And, looking into the performance using it, it will be looking into the benchmarking from the computer architecture perspectives. Definitely, you will find out that, Ptah modes are going to be nodes. B0s on the ClusterHAT will be acting as a drone nodes. Compute module 4 is going to be for the telemetry, gasping the information from GPS, IMUs. TRK1, it will be more for the control, the directions of the drones and the operations levels. So here, what we have inside the pod itself. So within the pod, there is a pod for the vision, especially if you have a camera with computer visions. There's a pod for the natural language processing. There's a pod for the telemetry. And even we are working even to make a pod for the flight controller, instead of having a separated flight controllers like PixHawk or, Navi 2 or, H7 based flight controllers. And, and the top of that, all of this will be in harmony working to each other. So for instance, the vision pod most likely going to be using YOLO. And YOLO, the grade that is working with the edge computing, like YOLO 4, YOLO 5. that will be fair enough to even look like an eye for the robotic elements, because end of the day, drone or UGV, it will be treated as fully autonomous. And of course, security between all of these little guys, it need lightweight crypto, like ASCON between of them within the board, but across the other drones or other elements, it will be post-quantum crypto for securing against quantum attacks like Shor algorithm and Grover algorithm, which is really like a little portion of the curriculum of this course is actually designing. Now, telemetry and performance pipeline. So if you look into the telemetry and performance pipeline, you will find out that, K3S clusters, they already have Z and Compute Module 4, which is both of them actually is ARM-based Cortex architectures. Then you're going to be talking through the serial or USB ports. You GASP the data to the telemetry pods. Then you handle it to the post-quantum crypto modules. Then, MQTTC, it will be handling the data to the other drones, as I mentioned in the early stage. And that's basically the whole entire end-to-end observed systems from the telemetry perspectives, as you can see. Here are some data that have been collected so far from the RAV-A of this system. So in a RAV-A, to speak to the drones, audio to text, it will take between 250 to 500 picoseconds. It depends on how it's fast, up to microseconds. NLP parsing is between 600 to 1200, but RabbitMQ, which is basically the handler broker of the bus, is between 80 to 200, and the control pod is between 300 to 600. If you add all of this together, you're talking about 1.2 to 2.5 milliseconds. It's interesting. Of course, it's a lagging delay. And I noticed that while we are flying the drones, actually, I'm talking between the UGV to the drones. But, if you add the pods, the latency and the milliseconds, it will be improved in a certain ways. Sometimes it will improve, sometimes not. And the Amdahl's law also going to be applied here. So they can see after a certain amount of pods, still nothing will be affected because, you got into the situations, which is a part of the computer architecture. So, so latency stay below 3 milliseconds. That's basically the target. We scale it up to 10 pods. After that, you don't need more pods. And of course, the students learn the bottlenecks in this particular experiments in the system. And resources utilization. So we agreed that, all of this share resources using the Kubernetes. So if you look carefully here, you'll find a compute module 4. It's for the BQC, it's taken a lot, if you notice, right? 20% for the telemetry, because it's just like gasping the information about the drones and health of the drones. And, the BQC and the drones for the NLP, that's actually the other part of NLP, it's little tiny things for the compute module 4. For Jetson Nano, because we already have also the GPU part, numbers is different. For ZW is different for resources because, we can use more resources, of course, in Jetsons, right? TRK1, for instance, it's really quite cool. And it's neck to neck, by the way, to Jetson Nano. There is a benchmark have been even provided and published by the company showing that, even it's a CPU versus you're talking about GPUs was full of metrics of processing elements, but the number is getting close if you look into the green computing, how much energy versus how much of computing we already have. Of course, this is based on Rhomus and, Grafana. And that's actually teaching students even what is Rhomus, what is Grafana, how can you collect the data and samples of the data from the distributed system and, broadcast it on a dashboard, and the dashboard how gonna look like so you can monitor within interval of 1 second to a couple of milliseconds about, the health of the systems, each node, how much time and energy it takes in runtime. Educational and research impacts. So you'll find that students learn the full stacks, hands-on, troubleshooting, dealing with memory, dealing with pods, because in the day, the pods it will be dealing a lot with memory, tangibility between of them and architectures, and also this work have been funded by the US Navy. So, we can prepare the students for the real world missions for securing edge deployment systems. So lesson learns. So we work in edge-based natural language processing, multi-level architecture, teaching systems performance, post-quantum crypto, which is worked seamlessly and even constrained in the devices, definitely because of the memory constraints. Cross-disciplinary project, to be honest with you. But looking at from the computer architecture perspective is actually gathering the data and information about the architecture, which architecture will be fitting this, which architecture is not fitting, which part it will be fit better, which part it need to be replaced or tweaked or added more based on the scalability that we mentioned. Here, literature review we started with hardware acquisition to buy the parts, system implementation, it took some big time, and of course debugging, gaining the approval, and even first deployment, because don't forget they were also building little drones. And by the way, some friends told me that even Russia is start encouraging their K-12 system to be teaching how to build drones for the little kids, actually, which is interesting, So that's why, adding the drones and UGV within computer architecture curriculum, that's really quite interesting because it shows people that, what is the real applications for the robotic futuristic applications and systems involving AI and computing. Future work, adding more visions, even using LiDARs and improving the optimizations techniques for decreasing the amount of memory used because that will be affecting on energy. Scalable more on orchestrations between the drones and UGVs and running full dynamic systems. Of course, accelerating using the GPUs and involving FPGA to build a heterogeneous swarm of drones and UGVs and robots elements that it will do the work based on multiple computer architecture platform, enhance observability, making the students actually looking into adding the dashboards of Grafana, what is the traces of the cache have been used and what is the scheduling algorithm have been used for scheduling the data resources shared between the nodes. Conclusion and takeaway, Ptah is linked to computer architecture, edge, and post-quantum crypto. Stack empowers students debugging, support heterogeneous edge node systems, and of course, using the Kubernetes, as I mentioned. Of course, I would like to thank you for your time. And I also would like to thank all of the people who worked together with us to make this happen from NASA Mines. It was a lot of competition that students win there. NAFC, which is a branch of the US Navy, and NEEC, which is actually funded the work, AFRL Research, and and Cal Poly Pomona, my home schools, and of course UIUC, as I work there as a scientist. Thanks a lot, and I'm looking forward to hear from any questions. I'm more than happy to answer. Thank you.